Okay, next we're going to hear from Robinett, AI6VN, and Paul Elliot, WB6CXC.
Well, thank you, Nathaniel, for the introduction and introducing me to the HamSci and the world of citizen science. I am the author of and started my return to amateur radio. I was introduced to the WSPR protocol, beaconing protocol, and over the last 5 years developed a software program that runs on Linux system called WSPRdaemon. And it was focused and remains focused on reporting on WSPR spots. But in the last year, I realized that, in fact, at last year's HamSci, I was introduced to the new generations of software development defined radios and the software of Phil Karn, K9Q. And this device, the RX888, which is a 16-bit SDR that you can purchase from China for $150, really changed my perspective both on WSPR, and it opened up the opportunity for WSPRdaemon, my software, to start to report the grape data measurements in the same way that it's been doing for years as we've been reporting on WSPR. So our goals in adding WSPR to grape functionality to the WSPRdaemon program was to be able to measure with Phil's software and this hardware to measure all of the WWV and record all of them, and CHU. So there's 10 time channels. We can record all of them simultaneously with the same sensitivity and accuracy as you can get from the grape 1 and 2. So this has to be GPS disciplined, of course, to do so. And there are other adjustments and accessories that need to be added to it to make it allow it to do so. Adding this functionality in no way impaired its ability to continue to measure all of the 15 ham bands simultaneously. So in one hardware device, you can be recording all the WSPR channels and all of the WWV and the time channels. Of course, the WSPRdaemon, the WSPR data is uploaded to WSPRnet, and the grape channels are uploaded to the same server that Bill Engelese maintains, the grape server, personal weather station server. So this is a complement and extension both to WSPRdaemon and the now 70 plus sites around the world that are running it, 20 of which already have these receivers, which are GPS disciplined and are contributing, have been contributing for the last several months to the GRAPE project. As you can see, the results that the uploads are the goal is to produce the same kind of data, the same as the GRAPE data, and as you see in the lower left-hand corner. But in addition, the WSPRdaemon site provides alternative ways to view this data and the WSPRdaemon data. So we are going to, I'm going to try to show briefly what you can gain from having a WSPR daemon receive site and with its complement, Paul's transmitter. This is an example of measurements we made during the October eclipse, where I drove out to Winnemucca, Nevada, and established a transmitter up there, W07I, in this map on the left, and a corresponding WSPR receive site near Las Vegas, in Pahrump, Nevada. During that same eclipse event, the GRAPE system in St. George, Utah, was recording the WWV transmissions. So in the right, you can see a comparison of the measurements we made with the WSPRdaemon and WSPR Sond transmitter against those that were made with the GRAPE receiver and the WWV. Both of these paths transverse the line of the annularity. So you can see there was a very good correlation between the two. So we believe that the measurements made with this device and our software are very compatible with and extend the capabilities in some ways of what they're doing with the grape receivers. So we wanted to achieve this high accuracy and sensitivity at a low cost. So as I mentioned, this is a $150 receiver. You do need to attach it to a host computer, Linux host computer. The ones that you can, if you have one of almost any recent vintage, it's powerful enough to do the processing. But if you don't, then we've been using a V-Link Chinese little mini PC, which you can get for $240 on Amazon. So the combination of this device and a host computer delivers all of the decoding and demodulation capabilities of both WSPRdaemon and of the grape functionality. A complete system, of course, like the grape system, requires a GPS disciplined oscillator. The Bogner at $175 is a typical example of, that's the standard GPS DO we use. The Tapper group, which we work closely with, also is under development, a lower cost GPS DO. So the goal is, of course, we want to continue to reduce the cost of the overall software. Everything in here is open source, well, except for this thing, but it's all open source software, and except for this hardware. This is a picture of the core components of a WSPRdaemon grape site. It consists of a mini PC on the right, the RX 888 connected by a USB cable to the host computer, and the Bogner. So those three components, you have to have a GPS antenna, like the puck antenna showed there, are sufficient to give you all of this capability in one small and low power package. This total power consumption of this receive device system is on the order of 25 watts on average. So you can be doing all of this with, I actually run this off a solar power system in Maui. So the additional, there are at any reasonable site, and a high performance site, you're going to need some accessories for your receive system. And Paul has developed a couple of components that are almost always necessary in a SDR receive system. One is a low noise amplifier. The SDR receivers are not, well, they're actually more noisy than your traditional transceiver. So in order to achieve the full sensitivity of a system, especially at 15 meters, 12 and 10 meters, there's too much internal noise in the SDR. And that's why I may think many people have had the experience of finding that their SDR is kind of deaf relative to their transceiver, especially on the higher frequencies. To address that problem, you need to put in a low noise amplifier ahead of the SDR, and Paul's device adds that feature. But of course, having an amplification increases the probability of overloading occurring from signals in the shortwave broadcast band and AM band. So Paul has included in his device a high pass filter, shelving filter, that suppresses the output of this device in the region below 10 megahertz. So you can, it also, because we run, this thing is capable of running at 129 megahertz, so you could do 6-meter reception on it. But in order to reduce the processing burden and the amount of data to deal with, we typically run these at 64 megasamples, which results in a 30 megahertz sample bandwidth, Nyquist limit. So Paul's filter adds a filter ahead of that, a very effective 30 megahertz low pass filter. So this is an accessory that is almost always necessary. It may not be sufficient. each receive site is unique. It involves a study of the system and the noise characteristics and the performance of the antenna. But these are typically essential at most sites. So this is the receive system that WSPRdaemon, this hardware, GPS receivers that allow us to receive and contribute to the GRAPE network and to WSPRnet spots in GRAPE data. But what we've also realized is that we had this wonderful multi-channel receive system capable of receiving almost every signals that are of interest to us. I've added super darn reporting recently, but we didn't have a corresponding transmitter. And the Eclipse in particular, being such a short duration, 4 minutes at most, if you were doing traditional band scanning and transmitting one band at a time, you're almost going to miss a lot of the bands, measurements on a lot of bands. So about a year ago, I suggested in my weekly call to Paul that it would be great if we had a transmitter that matched the capabilities of our receivers. And amazingly, Paul had a prototype ready for us last summer. We were able to deploy half a dozen of them during the October eclipse. And so I'm going to let Paul explain what he did and the capabilities of his WSPR Sound 8.
Thank you. Thank you, Rob. A question on the previous slide, there was a spectrum analyzer chart showing frequency response to the filter. Was that visible? Or it's just a black screen, but you could see the traces on it? Okay, good. I couldn't tell. Thank you. So the WSPR Sound is this is the second generation. For the October eclipse, we deployed a 6-channel version, but it's using what is now fairly standard technology. SI 5351 synthesizer chips. Just about every modern radio has those. And a little bit of software to control the frequencies and the modulation. Where our goal was to make this thing quick and easy to deploy, kind of plug and play, because we're going to rush these things out in the field in the back of a pickup truck. Just want to string out an antenna. Typically, in these systems, we're using 6 bands, 80 meters, see if I get them all, 40, 30, 20, 15, and 10. And we want to use a single antenna if we can, because who wants to put up a bunch of antennas in a hurry? So generally, we're using an 80-meter end-fed half-wave antenna. That's going to have decent resonances or matches on pretty much all the harmonically related ham bands above 80 megahertz. So, excuse me, not everybody used that, but a lot of us, I'm using those myself. So this is kind of plug and play. You use a computer to configure it. You can control what frequencies you're transmitting, when you're transmitting them. It uses the standard WSPR mode, or more often we're using FST4W. If you're not familiar with FST4W, it's almost the same as WSPR. Modulation's a tiny bit different, kind of cooler, but either one works. I think we like FST4W a little bit better for the data we get, but they're both good. So this will transmit either FST4W or WSPR. You configure it, tell it which frequencies you want, how often you want it to transmit. You give it a GPS disciplined oscillator, input it, 10 megahertz. You connect a GPS to it because it needs to know where it is so it can set up the grid square, and it needs to know what time it is so it knows when to transmit. 2-second frames, or pardon me, 2-minute frames. Plug in a 12-volt power supply. Actually, anywhere from 9 to 24 volts works, but we use 12 typically. And the antenna. And how do you get from 6 outputs or 8 outputs to 1 antenna? I'll do that on the next slide. So there's a combiner. You plug it in and it runs. So that was the goal, and I think we've achieved it. And let's see, do I do this to, yes. And you see on top, the Whisper Sonde, it's roughly rack mount size. Has 8 outputs on the left. It's got a GPS antenna input. It's got a reference clock input. Also has a built-in GPS splitter. So if you want to feed, as we're doing here, your GPS disciplined oscillator, you can connect that to this internal splitter, so you only need one GPS antenna. Got a USB port. That's for provisioning and also for monitoring and control if you want to monitor and control it. And Rob has sometimes set these up with a co-located Raspberry Pi that you can network into and then remotely keep an eye on things and change configuration if you want. But it'll tell you, the transmitters, what the power supplies are doing and what the GPS is doing and what it's transmitting. And then there's a power cord. Now on top to the left is a little box. You see 4 SMA connectors. Those are the 4, 80, 40, 30, 20 megahertz inputs that are coming out of the Whisper Sonde. The outputs are 1 watt square waves. These outputs are totally frequency flexible, 1 megahertz, anywhere between 1 megahertz and 50 megahertz. But we're going to run them on the ham bands, but you can run them wherever you want. But we run these outputs into what's I call a splitter combiner, which is, filter combiner, which is that little box sitting on top. There are 2 more inputs on the back. That's for 15 meters and 10 meters. That little box filters the square waves, turns them into clean sine waves, FCC ham legal sine waves, and then combines them out into 1 output port, which you feed into your multi-band antenna. So with the bodnar, with the filter combiner, power supply, GPS antenna, you've got a transmitter. And next slide. Here I'm just showing you the spectrum. It's a pretty clean spectrum. It's probably better than half the ham transmitters we currently own. You can see the 6 outputs of the combiner as they feed into an antenna. 1 watt output. The spurious is about roughly 60 dB down. And on the right-hand side of the screen, I just like this because it looks kind of neat. You can see the Whisper spectrum. Whisper uses 1 type of simple modulation, FSK modulation. And you can see the sidebands. Spurious, really, but it's part of the modulation artifacts, are pretty high. FST4W uses what's called Gaussian minimum shift frequency keying, minimum frequency shift keying. And there's filtering going on there as the frequency, instead of jumping from one to the next, it kind of gradually slides from one to the next. That reduces the modulation artifacts, and you can see that inner spectrum shows how much cleaner that is. This is low power, it's Whisper, everybody uses Whisper, and nobody really cares about the sidebands. But FST4W is cleaner, I like that, but that's because I'm a nerd. And well, that's about it. If there are any questions for Rob or for me.
I wanted to say that in the Whisper Sondes that are in operation, I have this particular model. Several sites, including our members, are being recorded by over 100,000 spots per day. 130 to 140,000 received reports from 1 Whisper Sonde. We had an enhanced version, one of our mates, it almost reached 500,000 reports. 10% of all of the Whisper spots came from 1 Whisper Sonde transmitter.
He was transmitting at a little bit higher power.
A little higher power and a very good location. So if you're interested in Whisper transmission, if you're interested in Grave, these 2 devices together it might be of interest to you. We will be giving a hands-on demonstration tomorrow at 11 over in the booth demo, right? And Nathaniel can guide you through that. Okay, thank you all. I think
thank you to everybody.